Hello folks, I hope you are doing well. In this video, we are going to be talking about higher derivatives. This should be a nice quick video, and we'll get right into it. So higher derivatives are another term for derivatives of derivatives. So if I have a function y is equal to x, say, my function is y. I know that the derivative of that with respect to x is equal to 1. So I can write it in the 1 notation with y prime, or I could have written this instead as in Leibniz notation, dy dx, but the same answer is equal to 1. Now, what if I were to take the derivative of this? So I could say the derivative of y prime, so I could say y prime prime, or I could say in Leibniz notation, it's a little bit stranger, dy by dx of dy by dx. Either way, I am going to be taking the derivative of my first derivative. The derivative of 1, or any constant, is equal to 0. Now, it's a little awkward to write it this way. So the general way to write the derivative of a derivative is just double prime like that, or d2y over dx squared. I tend to favor the first form rather than Leibniz when we're talking about derivatives of derivatives, but your mileage may vary. If we were to continue on, obviously, we can take the derivative of this. It's just going to continue to be 0 the farther we go, but we'll go triple prime, and then to avoid getting too ridiculous, usually you just start writing the number of derivatives or the number of times it has been derived in brackets. For this one, it just keeps on going. So d3y over dx cubed, d4y over dx4, d5y, dx5, etc. With that, let's move into the examples. I'm only going to do one example from the book. So example number 1 says find d2y by dx squared, or the second derivative of the function y with respect to x of our function y is equal to x to the power of 6. So we need to do it in 2 steps. First of all, we need to find the first derivative, dy dx. Well, dy dx of x squared, or x to the power of 6, is equal to 6 multiplied by x to the power of 5. There we go, that's our derivative. So y prime, or dy dx, is equal to 6 times x to the power of 5. And then from there we go on to the second derivative. So d2y over dx squared of our function 6x to the power of 5 is equal to 5 times 6, which is 30, multiplied by x to the power of 5 minus 1, which is 4. And that's basically it for higher level derivatives. All of the examples are just continuations of this. Maybe actually let's do one more example. Let's do example number 5, because this one is fairly different and might be tricky to do if you get a question like this and you haven't had an example. So in example number 5, we have if x cubed plus y cubed is equal to 5, find the second derivative of y using implicit differentiation. This is probably going to be a 2-pager. But we'll start with this. So first of all, we just need to find the first derivative. That shouldn't be too bad. So we will do what we've done before, what we did in the previous section. So d by dx of x cubed plus d by dx of y cubed is equal to d by dx of 5, or the derivative with respect to x of these 3 things. And we will take this one aside just like we have before. So the derivative with respect to x, of y cubed is the same as the derivative with respect to y of y cubed, multiplied by the derivative of y with respect to x. And the derivative of y cubed with respect to y is simply 3y squared, and we will keep our dy dx. So let's write the first step. So the derivative of x cubed with respect to x is 3x squared, plus the derivative of y cubed with respect to x we just found out from over here is 3y squared multiplied by dy dx. And the derivative with respect to x of 5 is just 0 because it's a constant. We now want to rearrange our equation, so subtract 3x squared from both sides. And we'll find that 3y squared multiplied by dy dx is equal to negative 3x squared. And divide both sides by 3y squared. And we find that the derivative of y with respect to x is equal to negative x squared over y squared. So that is the first step of this equation, or of this example. For the second part of example number 5, I need to once again use implicit differentiation to find the derivative. So we had, just to rewrite it, we had y prime, though I wrote it as dy dx, was equal to negative x squared over y squared. So let's find the second derivative. So y prime prime, y double prime is equal to t to y over dx squared. And as we have in the previous examples, implicit differentiation, we just treat the y as if it were another x, more or less. So we look at this, since it's y with respect to x, or y as a function of x, we are going to be using the quotient rule. The first thing I am going to do is I'm just going to take out that negative 1. Let's not worry about that for now. Now the quotient rule, if you remember, is the function on the bottom multiplied by the derivative of the top. So derivative with respect to x of the top minus the top multiplied by the derivative of the bottom. So the derivative with respect to x of y squared divided by the bottom squared. So y squared squared. This is the only one that's going to give us a little trouble up here. So I am going to take this little guy right here and bring it out here so that we can do it separately. So the derivative, I'll just say negative x squared multiplied by dxy. So that is the same as negative x squared multiplied by the derivative with respect to y of y squared, forgot my squared right there, multiplied by the derivative of y with respect to x. So that's going to give me negative x multiplied the derivative of y squared with respect to y is 2y, multiplied by dy dx, or in other words, 2xy dy dx. I'm out of space. dy dx. And now we're ready to put that back in there when it comes time to do so. So returning to our previous equation, we now have negative y squared multiplied by the derivative of x squared with respect to x, so that is just 2x, minus our big thing over there, 2xy multiplied by the derivative of y with respect to x, all divided by y to the power of 4. The first thing that I want to do here, you might get stuck. You look at this, I can't go any farther, but you can actually go farther because, I dropped my squared. Big mistake. How did I drop the squared? So x squared, x squared, x squared. Keep that x squared coming through. I know the value of the derivative of y with respect to x because we already found it. It's negative x squared over y squared. So I'm going to substitute that in now. So I have y squared multiplied by 2x. I should have rewritten that as negative 2xy squared, but there we are. Minus 2x squared y multiplied by negative x squared over y squared. It looks messy, but it's okay. All over x to the power of 4. From there, I'm going to multiply it out a little bit. Excuse me, multiply out the top. So I keep my negative out there. I should have kept it out there earlier. So I'm going to rearrange because by convention we go in alphabetical order with our variables. And then we have 2x squared, or negative 2x squared, I guess I could say, multiplied by negative x squared. So that's going to give me a positive 2x cubed, or pardon me, once again, 2x to the power of 4. And then I have a y multiplied by 1 over y squared, which is going to give me a just a y. Y divided by y squared gives me 1 over y. And then I'm going to keep my bottom still. Y to the power of 4. There's a few ways that I can deal with this, but I want to get rid of the fraction. Probably the easiest way, in the way that they do in the book and the way that I'm going to do, is by multiplying the top and the bottom by y over y. Y, oh y. So I need to multiply every single term by y. So that is 2x times y squared times y gives me 2x y cubed plus 2x to the power of 4 divided by y multiplied by y just gives me 2x to the power of 4, which is the reason that I did this in the first place. And then y to the power of 4 multiplied by y gives me y to the power of 5. My next step now is to factor out my greatest common factor on the top. So I have a 2x on both of those. So I'm going to factor out the 2x. So I will, actually in the interest of space and keeping everything up here, I'm going to go horizontal. Just for now, sorry if that's a little confusing. So keep on my negative. I'm now going to factor out my 2x. So 2x times y cubed divided by 2x just leaves me with the y cubed. Plus 2x to the power of 4 divided by 2x leaves me x cubed. I'm going to close my bracket. And divide by y to the power of 5. And you might be tempted to leave it here. You say, I can't go any further. However, if you remember right at the beginning, it mentions that x cubed plus y cubed is equal to 5. Well, x cubed plus y cubed is the same as y cubed plus x cubed. So we know that this portion right here is equal to 5. So we can rewrite that once again as negative 2x multiplied by 5 divided by y to the power of 5, which simplifies finally to our final answer of negative 10x divided by y to the power of 5. And that's really about it. As long as you know how to take a derivative, you can take the second and third and fourth and fifth or 100th derivative. I mean, the 100th might take a while, without any problem. Just think of a second derivative as the derivative of a derivative. And the third derivative would be the derivative of a derivative of a derivative, and so on and so forth. So if you have any questions about this, please do let me know. I'll try my best to help you with them, help answer them. And I hope you have a fantastic day. I'll talk to you later.